Well, let me iterate just a couple of principles here, and we'll move on to an even more concrete example. An example of the hypothesis testing process, again, marking that distribution. The alpha level, or the level of significance, is the probability value that's used to define the concept of very unlikely. Again, arbitrary, but widely accepted as 0.05. That critical region is composed of the extreme sample values that are unlikely, as defined by alpha, to be obtained if the null hypothesis is true. The boundaries for the critical region are determined by the alpha level. So let's check that out. And by the way, again, if the sample data fall in the critical region, the null is rejected. And it's a binary decision. There are no tweeners. It's just it's either okay or it isn't, or it's either rejected or it's not. It's like going to the airport. I always give this example. When you check your bag on a flight, the bag must be 49.5 pounds or less, let's say. If it's 50 pounds or more, you got to pay a lot of extra money. I think it's $200. And the airport is not really making decisions. They're just putting it on a scale. And if you've got a piece of luggage that's at 52 pounds, it's, hey, pal, you owe us $200. That's pretty rough. So what I've actually seen this happen. They advise people, get rid of some stuff, knock this down to 48 pounds so we don't have to charge you, and just buy, whatever stuff you threw away at Walgreens when you get there. It's just like that. We're not even making a decision. We're just observing, as we'll see later. There really are no decisions per se to be made. It's just a call as though it were on a scale. So the boundaries for the critical region, to determine the exact location for the boundaries that define the critical region, we use alpha, the alpha probability and the Z tables, the unit normal tables. In most cases, the distribution of sample means is normal, and we'll always assume that it is. And the unit normal table provides the precise Z-score location for those critical region boundaries. With alpha of 05, two tails, the boundaries separate the extreme 5% from the middle 95. Because that extreme 5% is split in two for the two tails, there's exactly 2.5% in each tail. In that Z table, you can look up a proportion of 0.0250 in column C, the tail, and find just by chance it's exact. It's 1,000,000 to 1, but it happened. That Z-score boundary is 1.96, and I'll show you this in a minute. Thus, for any normal distribution, the extreme 5% in a two-tailed test is plus or minus 1.96, and here it is. Here's those middle 95% high probability values, and you got plus and minus 1.96 that isolate the middle 95% from the 5% combined in two tails, 2.5% in each. And what I've got here, if you can see it, and I was really kind of hoping, to be able to draw on the thing. I don't know if it allows that or not. You can see that this is copied directly from the Z tables. Here's a Z of 1.96. It doesn't do it. Oh, crud. Sorry, I'm having a little trouble with the software. But here's the Z of 1.96. And, of course, here's the tail. This is column C right here. And I'm just looking to find 0.0250 in each tail. And by chance, this doesn't happen all the time, we happen to find a Z-score that does exactly that. I mean, that's a gift. It doesn't happen so neatly all the time. But sure enough, that'll mean the critical values of are plus and minus 1.96. What will that mean? We'll get an obtained value of Z from the problem. If it happens to exceed negative 1.96 out here or positive 1.96 out here, I'm going to reject the null hypothesis. Conversely, if that Z-score falls in the middle, somewhere between positive and negative of 1.96, I'm not going to reject the null hypothesis. And I hope you'll be impressed. There's no decision here. It's not like it involves thinking. Once I've established the goalpost, it either meets the criterion of following in these critical regions or it doesn't. There are no tweeners. There really are no judgment calls. It's just a matter of whether it falls in the white area or the orange area. And here are the goalposts, if you will, as defined by that alpha of 05 divided by 2, because this is a two-tailed test. So, and by the way, parenthetically, are there one-tailed tests? Yes. I want you to appreciate something. The critical values for a one-tailed test, I said one-tailed. For alpha of 01, let me take that back. For alpha of 01 in a two-tailed test are plus and minus 2.58. Now, where the heck did that come from? Well, that would be 0.0100 in the tail. It's combined. 0.0100 in the tails combined. Because with alpha of 0.01, how much do you have here in the middle? 99%. So with alpha of 0.01, it's 99% here in the middle. That leaves a total of 1% out here in these skinny little tails, right? Just a total of 1%. Well, what's 1% as a 4-digit decimal? Isn't it 0.0100? It is. Can I divide 0.0100 by 2? Yes. And what is that? Well, you can use a calculator if you want to, but 0.0100 divided by 2 is 0.0050. And as you'll see, the closest I can get is 0049. Now, strictly speaking, there's a tie. The z-score of 257 is 0051, but we just, by tradition, we'll just go with 258. Of course, in a test or something, I would accept either 2.57 or 2.58. But my point is, if I have 01, go with me on this, that's 99% that's in this white space, and leaving only a total of 1% out here on the wings, on the tails. I must divide that 1%, 0.0100 by 2, and I get roughly 0.0050. And again, we're going to go with 0.0049 because that's the best that the tables offer us.